Welcome to the first lecture of this course, which is curves and surfaces. So, this lecture, as I said in the introduction, it is a kind of a follow up of what I did in the first MOOC course on differential calculus of several variable. So, we will be using results from there, and our viewpoint here will be more geometric. I will not be working out everything very minutely and leave things to the assignments. So, whosoever attending the course, is very important that you solve the assignment problem, you join the discussion forum, you have any problem, anything, you clear it out in the discussion forum, and then go for the next module, because each module depends on the previous one. So, as I have posted, the first module will be on curves, and we will be mostly concerned on curves on R2 or R3. A curve on R2, this will be referred as planar curves, while these are curve on space, for obvious reason, is referred as spatial curves. Now, all of us have some idea what curves means. Let me recall some example. When you are in school, then you are often in coordinate geometry, you are often asked to find locus of a point. Let us say a very simple example, a point is moving in plane maintaining equal distance from a given point, say A B, and the equal distance is D, and all of you know what is the locus of this point. This locus of the points will be a circle with center A B and radius D. Now, often you say that okay, it may not be the entire circle, the point may not move the entire circle, it is a part of the circle. So, the locus is a part of a circle. So, this is the first time you see in coordinate geometry examples of curves. Similarly, if you do it in R3 and let us say a point maintaining equal distance from a point A B C, what this will be? Well, this will be a part of a sphere which is obviously not curve, but suppose I am moving. So, let us say here I have a sphere, so point is moving, let us say keeping equal distance from the origin, and it can move on this circle, and suddenly it may decide to change its course on the sphere and still move like this. So, finally, if I look at in R3, I will get a curve like this. So, So, there is a difference between geometry in R2 and R3, because R3 we have a extra dimension to move upon. So, this is the first example of locus. Next example you see in your calculus course, those are called level curves. That is, I have a very nice function f from R2 to R, and you look at all those points x, y, such that f of x y is equal to some given c. So, these are called level curves. And more examples, you see intersections of planes or surfaces. That also gives rise to curves like this, that suppose I have a cylinder here out here, and I have a plane cutting through it. The portion that belongs both to the plane and the cylinder, that gives rise to a curve in R3. So, you can imagine a cylinder is there, its plane is cutting, the portion that belongs the surface, outer surface of the cylinder as well as the, and also lying on the plane, that gives you a curve in R3. Okay. Now, when you discuss curve, we have to define it mathematically. So, I will consider curves in parametric form. What does it mean? So, here is the definition. A parametric curve is simply in R n, and for us n is either 2 or 3, is a map gamma from an interval a b to R n. So, this interval can be sometime open and sometime both closed. So, suppose let us say it R2, here is my AB, and I have a function which is defined from A to B, gamma t. So, t is here, each point I draw the graph and I get a curve gamma t. Example, let us say gamma interval is 0 to 2 pi to R2 gamma t equal to cosine of t and sine of t, and that gives you a circle. Let us say example 1. Next, I consider another function on the same interval perhaps. Gamma t is this time I consider cos 2t sin 2t. I will again get what? Think about it, you will again get a circle, but there is a difference between the first example and the second example. What is that? Here the speed of the curve has increased. What is speed? So, here what we say that speed has increased. in fact it is doubled. And what is speed? You know from your basic physics, the speed is gamma dot t and its absolute value. So, this is absolute value of d gamma dt, which is in this case is absolute value. Absolute value, I mean in R 2 absolute value is replaced by norm. If I do it for this one, for example 1, this is minus sin t cos t for example 1, which is equal to 1, and gamma dot t for is equal to, if you calculate, this will be 2 for example 2, because the 2 factor will come up. So, you see that this represents the same curve, but the point is, if you think like a point, it is the points moving on the plane, the point is moving in a speed double than the example 1. Another example, you can consider a special curve gamma t may be on the same interval, let us say cos t sin t t t in 0 to 2 pi. How does it move? It will move. So, on the planar part it is a circle and it is increasing with t. So, that will give you a helix. It will go like very nice. Now, for some reason we cannot study all curves. For instance, curve in R 2, suppose which is self intersecting, then studying this kind of curves needs special kind of technique or special kind of tools which are beyond the scope of this particular course. So, we will not study this kind of curve, we will study parametric, smooth, regular curves. What does it mean? Okay, curve for us is a map from A B to R n. This is a parametric curve. Smooth means gamma dot t throughout in this course denote gamma d gamma dt exist for all t in A B, and regular means gamma dot t is not equal to 0 for all t in A B. That is, derivative is non vanishing, that is, I have a well defined tangent. Okay. For example, if you look at this curve gamma t equal to t t square. What is gamma dot t? This is 1 2 t. So, gamma dot t is not equal to 0 for all t, let us say t in some interval minus 1 to 1. Now, If you look at this curve, which is say let us say t cube t 6, this represents same curve as t t square. Speed has been tripled, but this is not regular. Why? Because gamma dot t is 3 t square 6 t 5. So, gamma dot 0 is 0, while t is in -1 to 1. Whereas, this parametration is regular. So, a curve, same curve can have parametration which is regular and non-regular. So, we should be concerned about which curve should have regular parametration and which does not have regular parametration. That is one of our main point in the first lecture. But to state that as a theorem or state that as a result, I will first talk about a self invariance of a curve which is known as arc length. So, I have a curve gamma, let us say from A B to R n. Remember, n is always 2 or 3. I have 2 point t naught, let us say less than t, then arc length S t is defined to be t naught to t this way. What does it mean? Well, here is my curve, here is t naught and t is t. So, curve is like this. This is the point gamma t naught. What is the speed at this point gamma t naught? Gamma t is gamma dot t naught, and at this point is gamma dot t. I am looking at the absolute value of, okay, I am using both t. So, maybe I should use gamma u du. So, this is the speed, and I am integrating the speed from t naught to t, that gives me the length. That from time t naught to t, if I travel with the speed of gamma dot u norm, how much I travel? This is given by x t, and this is called the arc length. Now, you see I can have different parameterization of the same curve as we have seen. So, one needs to verify here that this quantity I am defining arc length is independent of parameterization. Okay. That is easy to check actually, and I will put this as an exercise after I define reparameterization. That same curve, what does it mean by reparameterization? So, what is the reparameterization of a smooth curve, because we are dealing with smooth curves only. Okay. Here is the definition. Suppose I have a curve gamma from an interval a b to R n. Then another curve gamma tilde, actually is the same curve gamma tilde from some other interval alpha beta to R n is said to be reparameterization of gamma if there exists a phi from alpha beta to a b, which is smooth, phi inverse exists and phi inverse is also smooth, such that gamma tilde t tilde equal to gamma phi t tilde for all t tilde belongs to So, what I have done? Let us see with the example of a circle. I have gamma t equal to cos t sin t, t in let us say minus pi to pi, that will give us a circle. Correct? And I look at the curve gamma t tilde equal to let us say sin t cos t, and this time t in minus pi by 2 to 3 pi by 2. You will immediately verify that if I take phi equal to pi by 2 minus t, then gamma tilde t tilde equal to gamma phi t tilde. This will represent the same curve, but the parameterizations are different. These two are different functions, right, and defined on different intervals. So, to end the lecture and to motivate you into the course, I will write down some assignment problems. I mean, it will be there in the assignment also, but you must solve them, because unless you do that, you will not be able to follow the next lecture. So, assignments is a part of this lecture. I want to emphasize this again and again. So, assignment problem, I just make some simple observation that reparameterization of a regular curve, we have defined regular curve is always regular. Next, arc length is a smooth function of t. Third, a parametric curve has unit speed parameterization, that is a parameterization such that gamma dot s, the speed is always 1 if and only if it is regular, and in this case, this is our fourth problem, if gamma tilde phi t equal to gamma t, this is unit speed parameterization, then phi t equal to plus minus s t plus some constant. This gives the unit pitch parameterization, though. So, sometimes the unit pitch parameterization is also referred as arc length parameterization, that we travel according to arc length, then it is unit speed. We will continue with the next lecture.